In this presentation, we're going to look at some of the up-and-coming wireless technologies which should inform the future of mobile systems. So what are some of the issues that we have just now that need to be solved for the future? Well, obviously a major issue is the increasing demand for bandwidth, especially for voice over IP, video over IP. More and more systems are moving towards delivering content, especially TV, video and even audio over networks. More and more we're seeing that the end connection is through some wireless interface. So there is a general demand for more bandwidth. Unfortunately, the bandwidth that we're using at the present isn't really being used to its optimal. So we'll see how we can change the basic architecture of our systems to allow much greater use and more efficient use of bandwidth. So that leads us on to better use of the bandwidth. At present we waste a great deal. To give you some idea, with inside about 1 meter square we only use about 1 kilobit per second at the present time, and really we need to be moving towards many more megabits for the same size of area. A major issue is mobility. For 3G and GSM type networks we have fairly good mobility where we can move between different cells and we do not lose our connection. Unfortunately, for many wireless systems, when we move between different access points, we lose our connections and we must re-authenticate and reconnect again. So mobile systems, and especially mobile IP, is a general issue that needs to be solved over the next few years. Power consumption too is a major issue, especially if we use wireless systems. They tend to use up power. So for example, a remote sensor might have a radio interface and might be out in the field, so that it must be powered by some battery. The more RF power we use, the more will drain the battery. So we need to make sure that we create systems which are power efficient, especially on mobile devices. Security is an area which is obviously a great concern. We've managed to fix the connection between the device and the access point, where we use TKIP encryption and session keys, and that has tended to make this connection extremely secure. Unfortunately, we have the whole back end to look at the whole authentication of the user, which access point they connect to. The whole back end actually is a major concern. There is a general issue with compatibility, in that some equipment still won't work with other types of equipment. We have standardized technologies, and then we have technologies which are near to standard, which are more manufacturer specific. Then there is the issue of tracking. With wireless systems we can actually track in much more detail than we can with existing systems. And then there is a general convergence. Should we converge on single technologies to make it easier for us to create systems, or when new technologies come along, should we give them the opportunity to grow and to create new areas? And then there's the general issue of scalability. The networks we've created really aren't scalable for our current systems, so we need to look at new architectures and topologies to support much better scalability. So what's our general focus for wireless networks? How should we be abstracting our networks in order to efficiently use the bandwidth that we have? And basically this is a good architecture where we can have small piconets in which we have highly concentrated bandwidth over a small area. In this way we use the available space to its maximum effect. Then we can have localized wireless area networks, which will generally connect these pico networks together, and then this will give us connectivity, say around a house or inside a building. And then between the buildings, between different towns and cities, we can have the glue which fits the whole thing together, and that's with wireless metropolitan area networks or cellular networks. This glue doesn't have to be high-speed connections but basically allows us to be able to interconnect our systems and provide the glue. Basically, the bandwidth reduces as we go out of this from high bandwidth, medium bandwidth to lowish bandwidth. So if we look at it in different abstractions, in a metropolitan area network, we might have cellular technology where the user migrates from one cell to another. So in this case we've used 2 to 3 different frequencies, and we can see here that we have no overlapping of colour for these frequencies. And then if we zoom in to each of these cells, we start to see our wireless networks on a localized basis. So it might be around a campus or between different households. And then inside each wireless area network, we can have our personal wireless area network. So what are some of the technologies that we have? Well, they tend to vary with data rate and also with their actual physical scope. For the small pico networks, we have Zigbee, which takes up to about 300 meters, Bluetooth only around 10 meters, and then for the future we have the possibility of ultrawide, which is highly concentrated but has an extremely high throughput. Then for wireless area networks, 11B, 11G and so on have taken off, and we can get a fairly good scope and a reasonable amount of bandwidth. Unfortunately, we can't really scale these networks on much more. Then for the wireless, for the glue, we can either have Wimax, or we can look at a cellular mobile technology, which is generally migrated from 2.5G to 3G and now on to 4G. Basically, it's difficult to actually keep increasing the speeds here, so we're likely to see that a lot of the applications which are now done through the mobile phone network will move towards this wireless arena. So what are some of the technologies which will actually drive forward the need for bandwidth? One of the areas is MIMO, and this is being standardized in the 802.11n standard. And one of the major problems that we have in any wireless network is to do with multipath. And in this case, the user has an antenna. The antenna might be a dipole, and it might spread its signals around. These signals will then be transmitted and then can be reflected off a metal object. So we see one path here, we see another path over here, and then a third path here. If we're very lucky, then all the signals will end up at the access point in phase and will actually add up, so we do not get any reduction in the actual signal. Unfortunately, what tends to happen though is that the waves actually arrive distorted or out of phase, and then when they're added up together, they can actually cancel each other. This can happen when we have 2 antennas across, say, a water inlet, in that we have a direct line of sight, and then we also have another reflection of the waves, and because of the physics of it, they can arrive out of phase and we can actually get a null caused. So we need to make sure our antennas are high enough so that we reduce the multipath problem. So we get fading, where we can move around and the signal will generally fade, and we also get interference of the signal. So this is a common problem, and it's becoming worse as more and more wireless signals are available inside the environment. It's also the case inside a house or an office. There is lots of metal, especially in the floors and in the ceilings, where we can have beams, and these waves will generally reflect off these objects. So the one way around this is that we can buy an access point with 2 antennas in it, and then we can implement diversity. We don't use the 2 antennas at the same time. What happens if we use diversity, then the access point will make a quick test and decide which is the antenna which is best to transmit and which is best to receive on, and then the access point will select that one. For a Cisco AeroNet, we can also define whether we use the left antenna or the right antenna. So in this case, this antenna might be better than this one, because typically what happens is that we only need to move an antenna a short distance to overcome the null problem. But an even better technology is actually to use MIMO. And MIMO supports multiple antennas. So we might have 3 antennas here, 3 antennas over here, and then we can actually transmit through the different paths for each data stream. So in this case we have 3 data streams, and then each will arrive, and it doesn't matter in what phase they arrive, we can actually multiply the actual throughput. So we can see here the 11N access point from Cisco has the 3 antennas. One is a directional antenna, the other ones are unidirectional or omnidirectional, and the access point itself will find these multipaths and use them as an efficient way to send data streams. One data stream might have a lot of data if it's a strong path. Other streams might have a little amount of data if they're weaker, but we can optimize it in this way. So more and more we actually see antennas which are made up like this with 3 antennas, or in 4 in this case, and we can see the access point has 3. We need to watch from a user point of view of these directional antennas, and that they concentrate the radio waves into a smaller region. So we need to carefully calculate the amount of radio power which is actually impacting on the user. And what we get from this is a much greater increase in throughput. So we go from 54 megabits per second with G towards 540 megabits per second with N, and it uses this MIMO path where we can create multiple paths between the access point and the client. One of the technologies that looks interesting to create the glue is called Wimax. And really Wimax is the answer to the problem of the last mile. So many users at home actually connect through an old twisted pair, non-shielded connection to the local exchange. This means that we have to be very careful about the actual bandwidth that we use and the signalling. And so ADSL has been created, and we're currently trying to push as much bandwidth through these old cables as possible. But there comes a limit to how far we can actually push this technology. A much better way is to replace this connection with some form of wireless connection, and Wimax should give us that answer. And basically we get antennas which fit onto buildings and onto poles. They are fairly directional so that we can intensify the signal between them, and are the answer to the ADSL and last mile problem. So they'll generally be used to interconnect wireless hotspots, provide 4G services which are high speed for mobile data and telecommunications, provide a backup for companies. So a company might worry that there was a fire on site and it might destroy some of the cables, even telephone cables. Then a wireless backup through Wimax is a good alternative and will obviously provide mobility. And what we get is basically a high speed, or we get greater distance. The further we spread the signal, the lower the bit rate that we can actually get. So the maximum range is about 70 miles and the maximum bit rate is around 70 megabits per second. But that is a shared bandwidth, and we typically get allocations dependent on the user's requirements. So we might get, for a line of sight, 10 kilometers at 10 megabits per second, but then this, for a non-line of sight shared access, we only get about 3 kilometers for 10 megabits per second. So the architecture of the future might be that we have mobile users connecting to Wimax. We might have organizational companies, organizational connections connecting onto Wimax as some sort of gateway. Hotspots themselves might connect in to the wireless network, and then the core of the network is still likely to be around the fixed connections, because these tend to give us very high speeds, typically more than 10 gigabits per second. So the line of sight backhaul is provided through Wimax, and then the main connection to the internet is still through some optical connection. And we might see home connections through this Wimax infrastructure. The GSM network has been a great success and has allowed us to use our phones and send text messages. 3G has been a lesser success, but it's obviously been used more. And we obviously need to look at the next generation of data services using the mobile phone network, and that's typically around 3G. And we can see here that the problem with the mobile phone network is it's quite difficult to really keep increasing the actual bandwidth. And we can see these technologies are starting to overtake the mobile phone type infrastructure. And 4G is basically based around 3G type technologies with some MIMO infrastructure where we can get multiple antennas with inside our devices to create multiple paths with the network infrastructure. An excellent application of wireless technologies is in location tracking, and it's possible to identify where an object is at any given time to many different levels of location resolution. So the first thing that we have to define is that how do we actually track an object or an entity using our wireless network. One of the simplest way is basically just to find out the cell in which an object connects to, and the object will generally connect to the signal strength which is the strongest. So for this we can actually find out that this device is actually within inside this cell, and then as they move they might connect to another cell so that we can pin down where an object is by just determining which access point it connects to. So we can have small cells, say within inside a building, where we can have multiple access points, and then we can determine where an object is by the access point they connect to. As they migrate through the building, then we can actually determine where they've actually been. And the same with the cellular network. So the mobile phone mast which our mobile phone connects to will define which cell that we're actually in. More and more these cells are becoming fairly small within inside cities, but are still relatively large in the outlying regions. Another method that we might use is that we might determine the round trip time between the antennae and the actual device. So in this case, if we use one antenna, then when we measure it, then it might be in this region here. So we can't really pinpoint it to any great accuracy. If we then measure the round trip time from two of our antennas, then we can locate it either being here or here. So we've now tied it down to a certain region. But if we now turn on three antennae, and we can typically see three access points or three mobile phone masts at any given time, then we can see we can triangulate it to a great degree, and we can pinpoint exactly where it is just by drawing a circle around the access point related to the time it has taken the signal to get there and back. Okay, so we can triangulate by measuring the time it takes, the round trip time to go to the device and back again, because this will travel typically at the speed of light, and we know that speed, so we can calculate the distance. We can also do this with signal strength, and that signal strength will generally decay in a certain way. If we can measure the signal strength from each of the access points, then we can actually measure roughly how far away something is. If the signal strength reduces, it's likely to be moving away. If it increases, it's likely to be coming nearer. And we can also measure if we can, with our antenna, measure the angle of the signal that's coming in. We can measure the angle at which it arrives, and then again through some sort of mathematics we can actually find out exactly where our antenna is, where our device is. With the angle, we actually only need one or two fixes to be able to determine with reasonable accuracy where it actually is, rather than the 3-node triangulation that we get with the round trip time. We can obviously use GPS, and GPS allows us, if we can see 3 satellites, again they measure the round trip time, and then they can actually calculate where the object is. Unfortunately, GPS doesn't work that well with inside built-up areas, inside buildings, and under things like vegetation. So what we typically do is that if we're lucky enough to have a device with a GPS chipset on it, then we could get one fix within inside our area. And then what we can do is that we can trace things like the signal strength or the round trip time to be able to judge where an object has actually moved to. Then sometime in the future we might be able to get a definite fix on the object, and again we could track. So this is a technique used by many mobile phone manufacturers, where they use GPS to get the initial fix, and then they will then track signal strength and round trip time. Another method that they might use is that a mobile phone company or a company within an organisation might map the RF space. So they would go around with an antennae and measure the signal strength within inside their building or within inside an area. And then when the device was being tracked, then they could actually just measure the signal strength from it, and they could actually work out where the device is likely to be. So we can see here, if they move here, the signal strength is likely to increase. If they move over here, the signal strength will reduce. If they move behind the tree, then again it will reduce. So this technique is used by many mobile phone companies, where they go around with vans with antennas and actually map the RF space. It can also happen within inside a building or within inside a room. You can map out exactly where the radio frequencies are, the radio signals are likely to be the strongest or the weakest. By measuring signal strength, you can actually get a mapping of the space. So to get that mapping, we might use a modelling tool such as this one, where we can put our access points in and then measure or estimate the power in each of the regions. We can see here are regions where there is very little wireless strength, but it's very strong over here. Or we might go out and actually do a mapping of the area to determine all the signal strengths within inside our space and add that into a database, so that if we can actually locate each of these access points with their signal strength, then we might be able to locate to a higher accuracy. Also, we can have handheld equipment where we can actually do an RF analysis of the space. So we have location tracking, and if we extend that on to be able to create an internet of things, then object identification is going to be key to the internet, so that we can not only locate, but we can also correctly identify objects. One of the most interesting for these is a pervasive technology called RFID, where we can wirelessly identify objects. Many systems currently use barcode technologies, and barcode is a fairly well developed technology, works extremely well in supermarkets where we need a line of sight connection, and then we can actually read the identity of an object. Unfortunately, we need a line of sight. We also need the surface to be viewable for the object, and barcodes only contain limited amount of information, such as the manufacturer and the product. RFID type technology doesn't require a line of sight connection. It can be embedded into a device, and it can also contain much more information, such as the manufacturing factory, a unique ID, and so on. And basically we have certain bands which are open for industrial, scientific and medical applications, and these are the 4 main bands that we use in RFID. And the choice is typically that at low frequencies we have a very long wavelength, so our antennas are extremely large, or we can have high frequency antennas. The wavelength for 11B, for example, 2.4 gig, is several centimeters. So our antennas typically have to be about this size here, which is about half a wavelength. And up here, the antennas are extremely large. So we can have high bandwidth here because we're using a high frequency. Typically the maximum bandwidth we can get is about 1/10 of the actual carrier frequency. So we should be able to get about 245 megabits per second. Down here it will only be a few kilobits per second. So the regions that we can have medium region here, or we can have low range, big antennas, or we can have small antennas. Some of the applications of RFID include stock control, where we can fit RFID tags to stock and automatically identify them. There could be the possibility of an automated checkout where all the goods were tagged with RFID, so it's possible to go out the checkout and it will automatically determine all the goods. Automated tolls are obviously a large application area where we can fit an RFID card into the car. Pet tracking, it's possible to put an RFID chip inside a cat, say, and then it can identify the cat. If we ever have two cats that are the same, we can identify one from the other, or we can even use location tracking. If we had a little RFID tag and it was strong enough, then we can actually locate if we've lost our pet. It can be useful for remote telemetry, where we can have sensors in the field and then each can uniquely identify themselves with some identification. Automated payments would get away with the problem of having to put a card into a machine and have a mechanical reader. We could have an RFID reader inside the machine, and we can just wave the card in front of it. Or we could actually ask users to have a special band which was RFID enabled. Food tracking is obviously a good application, where sometimes we have a perishable food such as fish, and we might want to trace exactly where the food has been. So it might have been caught by a certain boat, might have been passed on to a certain fishery, then onto a factory, then onto a reseller, and then to the final customer. If we find the goods have been lost at any time, we can actually track where it was lost, or if we find out there's been contamination, then we can find out who was responsible for the food item at any given time. We can go for anti-fraud, where we can fit RFID tags into objects and obviously onto ID cards. So the advantage of RFID is that we can have a unique product code. It gives us information on the product itself, the manufacturer, and some unique identity. For the RFID tag, we can burn in from manufacturer what its identity actually is, but mostly what happens is that we buy a special reader, a special writer, and we put a tag in, and it will actually reprogram the tag, something like a zebra printer, and it will create the identity on it, which will be a once only. So we write to it once and we can read many times. Once it's created, it cannot be changed. Or we can have tags which have a volatile memory, which means we can read and write to them at any given time. So an example might be in telemetry, where we might have an object identifier, and then for that object, say it was inside a freezer, we can have a basic description, its location, which freezer it's in, what the temperature is at a given time, and what it's been, the pressure and the humidity, and so on. So the tags themselves are either active tags. Active tags have a battery and a self-power source. They tend to be fairly large and are relatively expensive. Passive tags can be very small. We can see the microchip here, and the antenna itself gives us some physical distance. So with these, the range is limited because they don't have a lot of power inside them. They need an external source of power to be able to transmit back, but will last a long time. So passive tags typically have a short range. Active tags have a longer range because they have a power source. So active tags can typically provide location information using triangulation, where passive tags are typically cellular based. So we can have our tag. The tag could have a power supply, and then it can transmit quite happily to a reader. Or we might have a passive tag where we actually couple the radio energy into the device. It takes a little bit of power and has enough to be able to transmit back again. So the concept that we have is that we have a DNS present with the internet. We have an IP address, and that then matches to a domain name. We might know the domain name, and then it matches to an IP address. The future might be towards an object naming system where we have the RFID identifier, and then that will give us some information of the full details of where we can find the actual product. So we might pass the product ID to a website, and then that will resolve information on the product, full details of it, and so on. So standard EPC identifier is something like this. We have our header, then a manufacturer code, so that might be Kellogg's. We have an object class, might be cornflakes, and then we have a unique identifier at the end which will identify which packet of cornflakes it actually was. So if we stored this, then we can have some sort of lookup to be able to tell when the cornflakes were made, who supplied them, where they went to next, and when they will be out of date. So we get the concept of an ONS alongside a DNS. So this will allow objects to join themselves onto the internet as required, and then to have some lookup for these. So this is a standard infrastructure for it. We might have something that we're tracking. It has a basic reader. We process the tags, and then we have some back-end information service for these for the object. Then we might also have links to other databases. Say that if it's a product that involves many other products, we might have external links to these other products. So a proposed standard is to have this object ID. This is an example of one, and it defines the RFID tag in here. That can then get resolved into some physical markup, and then might point to some web server for information. So an example here of Gillette Mach 3. This is the unique ID code for that instance of the product. So for business to business, this is an excellent technology. So we have business here, business there. We make sure the customer isn't actually part of this process, because customers still think that if they have something with an RFID tag, then something is actually tracing them. The technology really isn't there for that to happen. But let's say we have an original source of fish, say, when it's caught, we read it in, and then when it leaves the factory pervasively, we can actually sense when it goes through the factory gates and trigger the event. Then it goes to a distribution center. When it goes into there, it might be on a pallet or on the actual food itself. Again, it can be automatically triggered that it's arrived there. It might be stocked on a certain shelf. Again, a reader will be able to tell which shelf it's actually on. It goes out of the distribution center, it's read again, transported into sales, and then once it's bought, then we can actually trace it again. So this allows us excellent updating of and tracking of where our object actually is. We can have tracking information here, stock control information, security fraud checking. We can find out where the object is at any given time, sales information. Whenever we sell a product, we can actually find out which product it was, where it came from, and when it was manufactured. And then we can have feedback if the customer wants some sort of information on the product through feedback information. So somebody could buy it and then provide us with feedback on how they found the product and integrate it much more pervasively. So let's look at a few examples of RFID technology. There are, in fact, many applications of this type of technology. Oil pipe identification, personal identification, blood analysis identification, medicine piracy, and so on. And these are just a small range of the actual true number of applications of RFID. One of the most interesting is that a professor in Germany managed to tag bees using passive RFID tags to be able to determine their behaviour. It's also used within stock control. In this case, Marks and Spencers have trialled tagging suits. So an RFID reader can determine that we have 6 blue and 1 green suit. Once it is bought, it goes through the reader and automatically a new blue suit is actually bought. And they have found that they can have 100% stock accuracy at any given time. A key factor is that the RFID tag is typically taken away from the actual suit when it's actually bought. So this shows an example of the tag, and inside the tag there is an RFID tag with its antennae. So it's possible for the company to keep this as a receipt, so that if a user brings back the tie, they can make sure that it was the actual original tie which they bought, else the RFID tag would be different. And we can see here on a DVD, inside there is a tag which identifies the DVD. At present, most of the tags are thrown away when the goods are bought. RFID is also used in medical applications. So we might have a hospital and we might have something like a fetal heart monitor. We can fit a tag, an active tag to it, and then we can actually trace at any given time where the actual fetal heart monitor is and to be able to determine it. Many hospitals also use active tags for key staff, such as surgeons, so they can find out where they are any given time in case of an emergency, and get them to go to help. More and more passive technology is actually being used because it is much cheaper. So several hospitals are trialling a passive technology with a wristband, where it's possible to go up to it with a PDA and actually scan the band. It might also be possible to create an RFID-enabled bed, which would actually detect when a patient went to it and audit them and then take it away. As much as possible, technology should be pervasive inside a healthcare environment. Anything which gets in the way of the professionals can actually disrupt their operation, and that is the reason that many healthcare professionals have not adopted IT systems, and that they have not been created to be able to integrate with their work. RFID technology might give the opportunity where a surgeon could go up to a computer, and then rather than having to log in, it detects an RFID signal from them and will automatically log in. RFID can also be fitted to the parts of a bike, say, so that if a crook broke the bike up, then it is still possible to identify each of the elements of the bike because the RFID tag is embedded into the casings. Another problem that we have is that when mobile phones or TVs are stolen, they might be changed in some way. If an RFID tag is embedded into the printed circuit board, then it's very difficult for them to change the actual identity of the electronic goods. And another application is in Legoland in Denmark, where parents register their child with an active tag, and then if the parents find that the child is missing, they send an SMS message, where's the child, and then the system will automatically return back through triangulation where the child actually is. And then the future might be towards magnetic ink, where the actual antennae is written as the text on a piece of paper. Then the microchip can actually be embedded into the paper itself. With this we can replace copper antennas with conductive inks.